Wait a minute. What if the most valuable place in all near-Earth space isn't Mars or an asteroid, but a thin, frozen strip at the moon's south pole, where sunlight and darkness behave in a way that changes everything about exploration? Near the poles, the sun moves in a low circle across the horizon, leaving some crater rims in near-constant light, while nearby basins remain in permanent shadow for billions of years. And these permanently shadowed regions reach temperatures below 40 Kelvin, cold enough to trap water molecules for geological ages. Water arrives from comets, asteroids, and the solar wind, and when it lands in those shadows, it cannot escape back into space. It becomes locked into the regolith, forming what planetary scientists call cold traps. Orbital missions detected hydrogen spikes at the poles, and in 2009, L-Cross proved the case by impacting a spent rocket stage into a shadowed crater. The probe flying behind it measured a plume containing water ice, dust, and other volatiles, confirming the South Pole is a real reservoir of usable material. On the moon, water is more than hydration. It is oxygen for breathing, hydrogen and oxygen for rocket fuel, and essential resources for life support and industry. Because if you split H2O using solar power on sunlit ridges, those gases can be liquefied and stored as propellant without lifting massive fuel tanks from Earth. The physics matters. The moon's gravity is 1/6 of Earth's, and the delta V to reach deep space from the lunar surface is far lower, meaning a refueling depot supplied from the South Pole could push spacecraft toward Mars or farther with drastically reduced launch mass. The South Pole also offers near-continuous illumination on certain ridges, creating stable power for mining operations, habitats, and communication systems, without the extreme day-night cycles that complicate other lunar sites. Picture how operations actually work. Solar arrays on a ridge harvest steady light, while robots descend into deep darkness guided by LiDAR and radar, drilling icy regolith, loading it into insulated containers, and hauling it back to melt, filter, and separate into water, hydrogen, and oxygen, before liquefying the gases into usable fuel. The challenges are real: abrasive regolith, huge thermal gradients, and the difficulty of storing cryogenic propellant in vacuum. Yet none violate physics. They are engineering problems we already understand how to approach with better insulation, robotics, and thermal control. Scientifically, those cold traps are also a time capsule, preserving a record of how water and volatiles moved through the inner solar system. By studying their isotopes, we learn how Earth acquired its oceans, and how often water-rich bodies strike rocky worlds. When you combine all of this, the South Pole stops being a poetic target and becomes an infrastructure hub. The only nearby location with frozen volatiles, sunlight for power, low gravity, and direct communication